the applicable or the best candidates for FDR applications are pavements with severe longitudinal and transverse cracking, pavements with poor ride quality, pavements with permanent deformation problems, pavement with graveling and potholes, and inadequate structural capacity. So we can use FDR pretty much for pavements in severely deteriorated condition. The critical processes for an FDR is of course the first is the pulverization, where existing HMA asphalt layers and a part of the granular layers are transformed into a uniform granular material, which we see follow from the pictures given in the slide, and followed by stabilization. And this stabilization can be done in different ways, which may include a mechanical, asphalt, or chemical stabilization. Compaction followed by application of a surface layer, which could be an overlay, microseal, cape seal, or chip seal type of applications, depending on the existing conditions. So what type of pavement alternatives we can get by this FDR processes? We can, I think, group them into 4 different categories. And the first category is pulverizing the existing pavement compaction. We get a layer that can be used as an aggregate subbase. There's no other application or any additional materials needed. But if you need a little bit of a stronger subbase, we can follow the same approach. After pulverization, virgin crushed aggregates, RAP or RCA, a cycle concrete aggregate, can be added and then compacted to obtain a stronger subbase. And the third alternative that we can get is after pulverization, we can follow up with a chemical stabilization. And this chemical stabilization can be obtained by adding one or more of the following alternatives: Portland cement, lime, fly ash, kiln dust, or calcium carbonate. Compaction is followed, and this application, this end product, can give us a treated base and a sub base for low to high volume applications, where especially if you want to get a more rigid pavement structure. And the final alternative is the asphalt stabilization. And in this case, we stabilize after pulverization by using emulsified asphalt or emulsified agents or foaming, and followed by compaction. And this gives us again a treated base or sub-base for low to high volume applications, which is a little bit more flexible than the stabilized layer by cement or chemical alternatives. And some of the critical steps to achieve best performance, again, which is the most critical consideration for sustainability. Some of the items for FDR starts with project selection. Of course, finding the right pavement for FDR treatment is extremely critical. Mixture design is required, and for tailoring mixed designs for each project and analyze existing materials and then change according to existing conditions. Selection of additives, use best working additives for in-situ conditions and target structural requirements. And achieving uniform gradation is another critical step, resizing the pulverized materials and adding virgin materials as needed to achieve a uniform gradation or target gradation. And finally, compaction is extremely critical, and it should always be included in the quality control and assurance steps, as it will have a critical impact on the performance of the FDR layers. And some of the final considerations, sustainability considerations for FDR applications, of course, performance is the most important. And how do we achieve performance? With some of the items that we just discussed in the previous slide: the project selection, quality and uniformity of existing materials, mixed design and selected additives, and surfacing type selection for the existing conditions and requirements, and finally construction quality. And since this is a specialized operation and requires specialized contractors, construction quality becomes an important consideration for achieving the desired performance. And some of the other considerations, sustainability considerations for FDR and generally for other in-place recycling techniques, is the curing and of course the traffic opening time. And finally, again, this is in general for all kinds of in-place recycling techniques, is we have to also look at the availability of virgin materials or plants that can produce alternative reconstruction methods as compared to in-place recycling techniques. I think with that I conclude my presentation, and I will give the microphone to Kurt.
Thank you, Hassan. We appreciate that. And again, I would like to remind all the participants that you're welcome to submit questions at any time. We are approaching now the final leg of our formal presentation, so now is your opportunity to start weighing in with some questions that we can address at the end of the webinar. With that information on end-of-life options for asphalt pavements, now we want to turn our attention to end-of-life options for concrete pavements, and to walk us through that is Dr. Mark Snyder. Mark?
Thank you, Kurt. I'm going to build on the issues that Hassan and Imad brought up in their previous presentations, particularly the general aspects of evaluating end-of-life for either pavement type. Hassan went through that on the asphalt side and related it back to what Imad had talked about in terms of the calculations. I'm not going to have much in the way of calculations or anything in this presentation, but we'll be talking mainly about the considerations, the factors that one needs to think about when trying to identify all of the different costs, environmental costs, economic costs, societal benefits, and so forth in considering the end-of-life options for concrete pavements. There we go. And as Imad talked about previously, the same three general categories of end-of-life options exist for concrete pavements as they do for asphalt pavements. Landfill and disposal, obviously, what we used to do routinely 50 years ago and now do relatively rarely now for reasons that we'll talk about shortly. Pavement reuse, applications where we're using that material in its current form, usually in current placement, not picking it up, although possibly picking it up and moving it, but generally in its current form with minimal, if any, processing. Occasionally some processing in place, rubblization being one example that is still considered to be reuse as opposed to recycling when you're leaving it in place, and we'll talk about that in a bit as well. And applications for reuse, examples of the various types of overlays. And finally, and I'm working backwards up the list as you've probably noticed, recycling, the process of breaking up the existing pavement, removing it, and processing it to produce recycled concrete aggregate, or RCA, which we're then using as a substitute for natural aggregate, virgin materials. And this is a process which has been around for a long time, more than 70 years, going back to relatively extensive use in Europe in the 1940s, after World War II, and even in the United States, a little bit building on the European experience. The first U.S. application was in the 1940s, also on Route 66, on U.S. Route 66. So some use of recycled material even in that great historic route there. Didn't do much more in the United States here until the 70s. There was a bit of a flurry of activity in the 70s and the early 80s, and again, kind of a lower level of implementation of recycling since that time until about the last 10 or 15 years, and there's been a much more increased, renewed interest in concrete pavement recycling as interest in sustainability has increased as well. All three of these options do have associated economic, environmental, and societal impacts that need to be considered. And again, the previous two presenters have done a very good job of discussing those factors in general terms, and I'm going to lay out here a few of the particular aspects related to concrete pavement recycling that should be considered. First of all, let's dispose of the disposal concept here. Disposal and landfill is defined obviously as hauling the materials off to a landfill where it's going to serve absolutely no purpose whatsoever. We're not talking about backfill here, we're talking about landfill. And there are obviously a number of costs associated with this, the demolition costs, hauling it off to the landfill site, transportation costs, and Hassan just talked about the costs of transportation on a cost or BTU per ton mile basis, and very similar sorts of things apply on the concrete side as well. And then the tipping fees, what the landfills actually charge for dropping the material there. And those vary quite widely around the country, particularly in the Northeast here where I live now. They're relatively expensive. They were reported as being almost $71 a ton, and that was 8 years ago. I'm not sure where they're at now, but the most recent published numbers were fairly significant. They range from about $30 to $70 a ton 8 years ago. And in addition to those costs, one could also consider the potential lost value of the recycled concrete aggregate that could have been produced. There's kind of an opportunity cost there, or a lost value of the aggregate that might have been produced if it was of suitable quality for doing so. And of course that value varies with the source concrete, the quality of that source concrete, and with the availability of local natural aggregate which would compete with the recycled material. So there's a lot of cost that is associated with disposal in landfill, just on a purely economic standpoint, let alone the environmental aspects of disposing in landfill and the consumption of that limited space. So clearly disposal and landfill as an end-of-life option is only rarely preferred over recycling and reuse, and we won't talk any more about it here. The next item is concrete reuse, and as I mentioned, this is using the concrete in its current form, usually in its current placements with minimal, if any, processing. And the prime example that we always come up with is going to be the placement of an overlay of some type. Dug through the files here. Here's an existing concrete pavement. They just did a light milling to the surface to remove and roughen the surface, and they're placing a bonded concrete overlay. This is here in Pennsylvania near Bedford, a picture I took last year. And this is the most common application, using as a base or a sub-base for an overlay, often an asphalt overlay, or for a new pavement as we're seeing here, an unbonded concrete overlay, or in this case a bonded concrete overlay. I noted earlier that rubbleization in preparation for the placement of a hot mix asphalt overlay does count as still reusing the concrete in place, because the process of rubbleization is one of many options that are available for the prevention of reflection cracking. It's not inherently necessary for the use of that pavement. It's just a selected approach. So rubbleization and then using the pavement in place as a base for an asphalt pavement still counts as concrete reuse. And the suitability of any given concrete pavement for reuse obviously is limited by the types of distresses that are present and their severity and extent. The photo off on the right here shows a fairly, let's call it moderately alkali-silic reactive pavement that, depending upon the rate of deterioration, may or may not be suitable for reuse in place as a base layer. Might call that a self-rubbleizing pavement, I guess. But obviously any kind of a pavement that has lots of joint deterioration in particular, where you're going to have a non-uniform support condition result from the deterioration that's present, or some soft spots. Maybe you've had some blow-ups and things that have taken place and they've been replaced by repairs or temporary repair materials or whatever, might limit the ability to reuse that pavement, at least without doing a bit of work on it first, kind of some restoration work and activity. Here's an example of a blow-up on another concrete pavement. This is one that actually was being reused in place. Again, this is right near my house, PA 50 here in Pennsylvania, and it's an area where there was a little bit of a blow-up there in that one area, and that you can see they've already cut that and they're doing some replacement on that to restore that area locally before placing an unbonded concrete overlay. So reusing the existing pavement with a bit of repair. Other evaluation conditions would include, issues concerning the structural integrity of the pavement or drainage issues. You may have a pavement which in itself is inherently in fine condition, but if there are known drainage problems that are going to limit the life of the overlay or the rebuilt pavement in that area, then that may be a question as to whether or not you need to actually go in and address those issues, which may prohibit you from actually reusing the pavement in place. It may become a recycling project in those cases. Geometric and safety concerns are the other issues that would limit the ability to reuse a pavement. Obviously, if you're building on top of an existing pavement with a thick asphalt overlay or an unbonded concrete overlay of some sort, you're creating additional, you may create additional needs in terms of raising guardrails, adjusting slopes. It may be impossible to do if you already have clearance issues under overpasses and so forth, where you'd absolutely need to do a removal locally. Maybe you can reuse the pavement up to the overpass, but then you need to do a replacement, partial replacement in the vicinity of the overpass itself. So those kinds of things can limit the ability to reuse existing pavements, even when they might otherwise appear to be good reuse options. So if we look at the overall environmental and economic impact of concrete pavement reuse, as with asphalt pavement reuse in general, I think that the potential benefits are usually the highest of all of the end-of-life options, because we're not expending a lot of energy, we're not consuming materials that will be required for rebuilding a pavement, and we're not hauling materials. We're eliminating the energy and the costs that are associated with disposal. And we usually have a relatively short construction window. If the existing pavement is in place, you're not rebuilding subbase, you're not doing drainage, you're basically just overlaying or building on top of that. It becomes a much shorter construction duration, often lower cost, lower societal impact. So generally a very, very highly desirable end-of-life option if it can be accomplished. As Hassan noted, these benefits can be partially offset or even completely offset if we have a shorter performance life or more frequent maintenance is required. And examples where this comes to play typically are when we reuse a pavement without addressing inherent foundation or drainage deficiencies that are going to shorten the life of whatever we do on top of it. And again, to reiterate what Hassan said, we have tools at hand with the life cycle assessment and life cycle cost analyses and various pavement performance analyses using performance models that the various states and even in our design procedures, our national design procedures, we have those as tools to help determine the suitability of these pavements for reuse. That brings me to the third of the three options, and this is where I'll spend a little bit more time because there's a bit more to talk about here with recycled concrete aggregate. And as we mentioned before, recycled concrete aggregate is where we are removing and processing the concrete pavement to produce a replacement for natural aggregate or virgin aggregate. And there's a number of potential applications for this. We can use it back into Portland cement concrete pavement. This is a photograph here of Interstate 10, I believe it is, down around Houston, Texas, where they use 100% recycled concrete aggregate in the production of that pavement. It's a CRC pavement, has both crushed concrete coarse and fine aggregate. I believe that's about 15 years old now and still in very good condition. So single lift concrete applications, two lift, we're seeing it more commonly used in two lift applications in the lower lift of a two lift pavement. Can be used back in hot mix asphalt as Hassan mentioned earlier and Imad mentioned. Tends to have a little higher absorption. It's a little more asphalt cost there, but it has been done successfully in hot mix and warm mix asphalt. The most common application far and away is into unbound and unbound base layers, occasionally stabilized base layers, and these layers may be drained or undrained. There are some concerns when you use a drained unbound material, and we'll talk about those here in a little bit. Backfill and embankment material, riprap, as you see down here, for erosion control. And there are many, many other sorts of options and applications that have been used as well if you look through the literature. The specific applications that one might use crushed concrete for are sometimes limited by the quality of the source concrete. For example, if we have materials related to stress, alkali aggregate reactivity, or freeze-thaw, decracking types of issues, or mortar-related freeze-thaw issues, inadequate air void systems, you may have some question about using that back into a concrete mixture, although it has been done successfully in some cases with appropriate modifications to the mixture and appropriate treatment of the crushed concrete. It still gives people a warmer, fuzzier, higher degree of confidence to put it into an unbound layer. And then there's a whole question about the source of the material. And paving concrete we tend to have a pretty good handle on, and it tends to be relatively free of contaminants other than minor amounts of joint sealant material and the occasional piece of steel. Building demolition as a source of aggregate for pavements using back into a concrete mixture can be problematic because of the inclusion of drywall, gypsum, brick, lightweight materials, things that may interfere with the set and so forth of the concrete. One needs to have a better handle on the quality production involved there. You saw this slide previously, and it just kind of reiterates what was said earlier. Most of the applications we see being used for crushed concrete do fall into that aggregate category as a base or a sub-base. A little bit here into hot mix, warm mix, a little bit into new, a little bit into fill, riprap, and other applications as well. But a lot of it being used, and as I don't remember if it was Hassan or Imad that pointed out only about 1% of the asphalt's going to landfill. I don't know exactly what the number is on the concrete side, but it's comparably very, very low. More concrete from building and demolition goes to landfill than from concrete pavements these days, far and away. The economics are highlighted here in this slide.